In this video, we're going to continue with a look at orthogonality, and we're going to start building up a theory based on that kind of information. So let me start with the following. A set U1 up to UN, I probably should call this M, subset of vectors of Rn, this set is called, or is, an orthogonal set. If each distinct pair of vectors is orthogonal. That is, ui dot uj equals 0 whenever I does not equal j. So a quick example to illustrate this. Determine if (1, -2, 1) 0, 1, 2 and -5, -2, 1. So we want to determine if that is an orthogonal set. And there's no real quick way other than to take the dot products of every possible pair of vectors in here. So there's three possibilities here. I'll take 1, -2, 1, and I'll dot it with 0, 1, 2. Of course, that equals, remember how this works. I take 1 times 0, I'll write it out, 1 times 0, so the first coordinates, plus the product of the second coordinate, so I have -2 times 1 there. And then finally I have plus 1 times 2. And this does, in fact, equal 0. 4 minus 4 is equal to 0. So let me see how it does with the third vector in the set. That one was -5, -2, 1. So this equals 1 times -5 plus -2 times -2 plus 1 times 1. And that's -5 plus 4 plus 1. So that equals 0. And I have one more pair to check before I say that this thing is orthogonal. The last that I have to check is 0, 1, 2 dot -5, -2, 1. So that's 0 times -5 plus 1 times -2 plus 2 times 1. And I get 0 minus 2 plus 2 equals 0. So, is it an orthogonal set? Well, the answer is yes. That leads me to a theorem. If S equals U1 up to UP is a set of, now watch what I write here, vectors, but when I write this notation here, I'm telling you that they're non-zero vectors. So I'm eliminating the zero vector as a possibility when I write that notation. So anyways, if this is a set of non-zero vectors is orthogonal, then S is linearly independent. So for the proof, we'll do the basic thing. Suppose C1 up to CP are real numbers with C1U1 plus dot 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 plus CPUP equals the zero vector. Now what I'll do then is I will pick any of them. I'm going to use U1. If I take U1 and I dot it with that entire expression, that is the same as U1 dotted with the zero vector. And we already know that the right side will still be the zero vector. But on the left, using all those properties of the dot product and everything, we'll end up with something like this. C1 U1 dot U2 U1 plus C2 U1 dot U2 plus dot 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 plus CP U1 dot UP. Now it's an orthogonal set, so we know that UI dot UJ equals 0 when I does not equal J. So if you look throughout this, then everything in this expression will be 0 except the very first term, because this is 0, down here is 0, everything's 0. So we end up with C1 U1 dot U1 equals the 0, I'm sorry, not the zero vector, sorry. I made a mistake up here too. It's just 0. Well, U1 is non-zero. We must have that C1 was equal to 0, because what you'd have is C1 times the norm of U1 squared equal to 0, and I can divide both sides by the norm of U1 squared, since I know that's a non-zero number, and that will be equal to 0. In other words, C1 equals 0. I don't know if it was clear enough when I first did it. Next, you can do U2 dotted with that linear combination. So I know the right-hand side is 0. On the left-hand side, the same thing's going to happen, and all you're going to be left with is C2 U2 dot U2. And that will, of course, imply that C2 equals 0, since U2 is not the zero vector. So keep this up. So keep doing it for all the indices. Next, you do it for U3, do it for U4. But anyways, when all is said and done, we have C1 equals C2 dot dot dot. We get that all of these scalars is equal to 0. If S is as in the theorem, then we know that the span of those vectors is a subspace of R to the n. Let me give a definition. An orthogonal basis for R to the n is a basis for R to the n that is also an orthogonal set. And we're used to this, like in in R squared, we have that this is equal to the span of 1, 0, comma, 0, 1. You can see that they're orthogonal to each other. They're perpendicular. In R3, we have the span of 1, 0, 0, 0, 1, 0, and 0, 0, 1. Once again, an orthogonal set. So there's something very useful in having the basis vectors be perpendicular to each other. Another theorem. Let U1 up to UP be an orthogonal basis for a subspace W of Rn. Just to make sure W is equal to the span of those vectors. So W is a subspace of Rn. Now, for each y in W, write the y as a linear combination of the vectors. Then, so, if I pick any element in W, then I can write it as a linear combination of those basis vectors. Then I actually know what CI equals for each of the i's. I'll know that it's y dot ui all over ui dot ui. Remember, CI is a scalar. When I take a dot product, it's a scalar. When I take a dot product, it's a scalar. This whole fraction is nothing more than a real number. So anyways, and this is true for each I equal 1 up to P. Let's look at the proof. So we'll start exactly what I said we would start with. So we'll write I as a linear combination of the vectors in the set. And then if I take y and dot it with ui, I'll get that set. All right, let me go ahead and multiply this set on the right hand, or this expression on the right hand side out. We'll get C1 U1 dot UI plus dot dot dot. I think I'm going to put CI UI dot UI plus dot 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 plus CP UP dot UI. So I should probably say that UI is picked. I don't care. UI is one of the vectors there. Now, what we have is that everything on the right-hand side becomes 0 except for the ith component. So I'll get a 0 there, I'll get a 0 there, I'll get a bunch of zeros, 0 here, until I get to CI dot UI plus 0 plus dot 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 plus 0. Everything will zero out because of the orthogonality of the set. So I'm left with y dot UI equals CI times UI dot UI. Since we have a vector or a vector space, these U's come from a vector space, I can divide both sides by that number, UI dot UI. Do the same over here, UI dot UI. And what does that give me? These all cancel away. CI equals Y dot UI all over UI dot UI. As an example, let's let U1 comma U2 equal, I guess I should make this bigger, 2, negative 3, comma, 6, 4. Now you can see if you take their dot product, it'll be 0. So you have two linearly independent vectors in R2. So we know that this is an orthogonal basis for R2. So let y be any vector. Well, I don't want to say any vector, but I just want to give you an example of how this works. So what I want to do is write y as a linear combination of the u vectors. So what you want to do then is use the theorem that we just had. If y is equal to c1 u1 plus c2 u2, we know how to get c1 and c2. C1 equals y dot u1 all over u1 dot u1. 9 times 2 is 18, plus negative 7 times negative 3 is 21. That gives me 39. Now let me do u1 dot u1. If I do u1 dot u1, that's just basically squaring each of the components. So I get 2 squared plus 3 squared, so that'll be 13. And then we put the u1 after. Well, I don't put the u1 after it. That's what will go in the line above this. That's just equal to 3. C2 equals y dot u2 divided by u2 dot u2. Let's see what that's equal to. I'll start with the y dot u2. So I have 9 times 6 is 54 plus negative 7 times 4. That's negative 28. So 54 minus 28 is 26. And then u2 dot u2. So I'll do 6 squared is 36 plus 4 squared. That's 36 plus 16 is 52. u2. I don't know why I keep putting that. Because I'm going to check this in a minute. So let's check it out then. What I just have figured out is that y equals 3u1 plus 1/2 u2. Let's check. The y was equal to 9, negative 7. U1 was 2, negative 3. And the second vector was 6, 4. Let me continue. Multiply the 3 through, I'll get 6, negative 9. Multiply the 1/2 through, I'll get 3, negative 2. Make that a positive 2, that's not a negative 2. And then when I add them together, I get 9, negative 7, as promised. Let's do it again just for a little more practice. U1, the dot product is extremely important in what we're going to do. This particular formulation of the fraction that we have is going to be used throughout the rest of this particular material. So here, let's do some three-dimensional vectors. We have 3, negative 3, 0, comma, and we have 2, 2, negative 1, comma, and then we have 1, 1, 4. Now, if you get good at the dot product, you can basically look things over and see if it actually is orthogonal. Let's check it real quick. I can tell that these two vectors are orthogonal because 6 minus 6 is 0. I can tell that the first vector and the last vector are orthogonal because 3 minus 3 is 0. Notice that 0 doesn't come into play except to make the last component 0. And then finally, when I take the dot product of the last two vectors here, 2 plus 2 minus 4 is equal to 0. So we know that this set is an orthogonal basis let y equal 5, negative 3, 1, and the job is to write y as a linear combination of the u vectors. So what we want to do then, let's call this the solution. We want to set y equal to c1 u1 plus c2 u2 plus c3 u3, and c1 equals y dot u1 over u1 dot u1. Let's go ahead and do that one. So start with y dot u1. So I'm taking this vector 5, negative 3, 1, and I'm dotting it with negative 3, negative 3, 0. Let's see what we get. 5 times 3 is 15, plus negative 3 times negative 3 is 9, so I'm going to get 24, divided by, now u dot u, so I'll take 3 squared is 9, plus 3 squared is 18, C2, let me simplify that a little bit. If I divide by 6, I'll get 4/3. C2 equals, now I'm going to do y dot C2, they call it, no, U2, all over U2 dot U2. Let's take a look at y dot U2 first. So I'm using this vector with this vector here. So I'll start 5 times, whoa, didn't expect that to happen. 5 times 2 is 10, plus negative 3 times 2. So 10 minus 6, I'm at 4, minus 1 more will make that 3. And then I've got to do this vector dotted with itself. So I'll get 2 squared plus 2 squared plus 1 squared. That's 5. And then finally, C3 equals y dot U3 over U3 dot u3. Let's see what happens there. I'm taking this vector now and dotting it with this last vector, 1, 1, 4. So let's see what happens. 5 times 1 gives you 5. Negative 3 times 1 gives you negative 3. So 5 minus 3 is 2. Plus 1 times 4 is 6. And then u3 dot u3 will be 1 squared plus 1 squared plus 4 squared. I believe that's 18. So this is actually 3/9, which is 1/3. Well, it's nice. They're all over thirds, so that makes me feel more comfortable. Let's check. So what I need to happen is that 5, negative 3, 1 needs to be 4/3 times u1. And where was that? 3, negative 3, 0. And then I had 1/3 times the second vector. That was 2, 2, negative 1. And then finally, I have 1/3 times the third vector, which is 1, 1, 4. Let's just do it by hand. You can check it perfectly yourself later, but I'm going to start here. 4/3 times 3 gives me 4. 4 plus 2/3 plus 1/3 does equal 5. So that works. The first component works. Next, we have 4/3 times negative 3, which is negative 4, plus 2/3 plus 1/3. So negative 4 plus 1 is negative 3. And then finally, for the last piece, I don't have anything. 4/3 times 0 is 0. But then I have 1/3 times negative 1. So I get negative 1/3 plus 4/3 will be 3/3, or 1. Next, let's take a look at something called an orthogonal projection. So for this, here's what I want to do. Let u be a non-zero vector in R to the n. And let y be a vector in R to the n. Here's what we want. We want to decompose y into two vectors. This is how I want to do it. Y I want to write as the sum of two vectors. And I think the other one I'll call it z. Where y hat is parallel to u, that is, y hat is a multiple of u, and z is orthogonal to u. We'll use r squared for inspiration, if I can ever write the thing. Here's what the setup is. Basically, what we're going to have is I'm going to have a vector y, and I'm also going to have a vector u. Now, the art of projection is you pretend like you have a flashlight above, directly above the vectors themselves. If you were to shine the flashlight onto these vectors, this y vector would cast a shadow. How big? Onto this vector u. Now, it would cast a shadow directly down this way. So this vector, the way I drew it, is not long enough. So the idea is to scale u. So then I'll pick some sort of a real number like alpha. Alpha u will be u but longer, long enough so that this projection can happen. And in fact, the way I drew it is not exactly correct. Let me continue. Let me actually increase this. What we want, let me increase this vector. In fact, let's just say it's on a line. Now the projection will look like this actually. So I guess it's not directly above, but you can see it's orthogonal in nature because we're projecting so that this is a right angle. So I was mistaken. This vector, this long vector, and let me in fact draw something. Give me my pen, and let's make it fatter so that I can draw a big fat vector here. There it is. Now let me go back to small. This vector here will be our alpha u. So there, it was made long enough. Now, I think a better picture might be the following. Let me draw a picture this way with them sort of rotated so it's easier to see. So I'm going to call this alpha u. That's going to be my y hat. There's my y. Now, this little distance between them here, what I want to do is draw a perpendicular vector to u. Go ahead and get it to do that. We're going to call this vector z. And I only made it so long as it's the same as this length here. That's how long z is. Now, if you remember the way we add vectors in the plane, I have z is this vector and y hat is this vector. Well, this vector plus this vector equals this vector here. So we have y equals y hat plus z. And from this I can get z. Z equals y minus y hat. So those are the two vectors. So what I want then is the way it's drawn, alpha u is clearly a multiple or parallel of u. So I've got that part down. The other part then, so if we need z dot u to equal 0, this is what we need to happen. So how is that going to happen? Then we're going to have y minus y hat dot u will equal 0. Now let me go ahead and do y dot u. I keep wanting to put a u1, but there's only one u we're talking about here. Minus y hat dot u equals 0. Now I'm going to go ahead and replace y hat with alpha u. Remember that y hat was equal to alpha u. Let me go ahead and add alpha u dot u to the other side. So I get y dot u equals alpha u dot u. And if u is a non-zero vector, I believe that I did say that u was non-zero, so I'm going to divide by u dot u. So let's just make sure of this. U is not the zero vector, so I know I'm not dividing by 0. And what do we have when all is said and done? All these u's cancel out on the right. Alpha will equal y dot u over u dot u. So that'll be the alpha that I have. And so the z will equal y minus y hat. That equals y minus y dot u all over u dot u times u. Remember, this part right here is the alpha that we wanted here. So when I want to decompose my vector then, what did I have? We had y then would equal, let's go back up to what it was equal to, y hat plus z. The y hat was whatever alpha needed to be. We already know what alpha is supposed to be. Z was y minus y hat. And the alpha, let's see what we had, y dot u over u dot u, and that's times u, plus y minus y hat. This piece right here is parallel to u, and this piece right here is perpendicular to u. So that's the breakdown that we want for our y. Y hat is called the orthogonal projection of y onto, you can say u or you can say L. In calculus, they'll say it is onto u, and we'll actually write the projection onto u of y, and that's equal to y hat. And notice, you could say it's L or U. The alpha that's being used, let me come back to it. Remember, the alpha that was being used was there to make this vector long enough, or if the vector's too long, it can shorten it to the right size. Let's compute the orthogonal projection of y equals 1, 7 onto u, which equals -1, 3. So remember, that's the alpha that we want. That's y dot u all over u dot u. We want alpha u is actually what we want, but let me go ahead. Let me do it this way. I think I'll do y hat, there's our projection, is equal to alpha u, and that's equal to all that stuff times u. And so let's do these dot products. I'll start with y dot u. I got 1 times -1 is -1, plus 7 times 3, so that's 20. Then u dot itself is 1 squared plus 3 squared, that's 10. And what was u? -1, 3? So this equals 2 times 1, 3, which equals 2, 6. Okay, what I've done here is I've drawn the vectors in a program called GeoGebra. As you can see, there's my y vector, which is 1, 7. There's my u vector. And I couldn't make a y hat in this thing, so I just used the letter h, and that's the -2, 6. Here's the vectors. You see there's y, and u's bit short for what we need to do, so h is made to be longer. Let me take that into our discussion. and bring it down into here. And so from this, hopefully you can see what I was talking about. You might have to turn your page, but as I go here and draw this, you can see that certainly looks perpendicular, doesn't it? So there's my y, there's u, and then this thing that's longer is the y hat. So y hat is the projection. That was actually negative 2, 6. So you can see it goes to the point negative 2, 6. Now that wasn't everything. Z, although I did what was asked in the question, z is equal to y minus y hat. So ry was 1, 7, and y hat was negative 2, 6. So what do we get then when we do this? 3, 1. Let me redraw this graph, though, with z in there as well. The input that it expects you to put the end point in there. And let me come back. Z was 3, 1, 3, 1. And you can see there it is. Let me go ahead and bring this into the discussion. And as you can see, let me go ahead and draw this dotted line again. And if you want to, these vectors can be moved to where the bottom of them start anywhere you want. You can see that this is just like z up there. So there's my y, there's my u, and there's my y hat, all displayed in one picture. All right, let me redraw a little bit of this. Not what I did. This is a new example. So once again, we'll have a u like so, and then we'll have a y. Now, if I need to, I'm going to draw a line through the origin that it contains the vector u. So we'll call this L, which is actually equal to the span of u. The span of u makes longer or shorter u's as needed. And then we have this projection onto that line. So if you want to think about it, that's actually a projection onto the line. So this right here, this vector is y hat, which equals alpha u, as I've said a few times by now. The distance between y and the line L is given by y minus y hat. Now, how are we figuring that out? The distance between them is actually the distance between the endpoints of these vectors. They obviously touch each other, so you would say, oh, the distance is 0. Not true. That's not what we're talking about here. We're talking about the ends of the vectors. What is the distance between those? So this is definition. Let me put that down. In our situation then, take a look at this. Y minus y hat equals y minus alpha u and that equals y minus y dot u all over u dot u times u. As an example, let's let y equal negative 3, 9, and we'll let u equal 1, 2. So the distance between y and a line containing u is y minus, and now let's go ahead and put those numbers in, y dot u all over u dot u times u. Let's throw all those numbers in. The y that they've given me is negative 3, 9. And while I'm at it here, let me make these norm bars longer to accommodate my vectors. What's next then? We have minus. Now what's y dot u? Let me see, I have negative 3 times 1 will be negative 3 plus 9 times 2. Negative 3 plus 18 is 15. And then u dot u is 1 squared plus 2 squared. That's 1 plus 4, that's 5. And then my u is 1, 2. Well, let's go ahead and take a look. We have negative 3, 9. That's 3, so I'm going to have minus 3, 6. That will equal negative 3 minus 3 is negative 6. 9 minus 6 is 3. That equals the square root of 6 squared plus negative 3 squared. And that'll be 36 plus 9 will be the square root of 45. Or for those that like the simplified version of it, 3 radical 5. And remember, the distance will be the distance between the end of this vector and the end of this vector. So it's really, if you want to think about it, it's the distance between the points negative 3, 9 and 3, 6.